Hello, I am an antenna engineer, and in this video, I am going to show you a couple different types of passive reflectors for extending the range of a cell phone. More importantly, I am going to show some analysis and test results that quantify the amount of signal enhancement you can expect from these small lightweight reflectors. The demonstrated results will show that these small reflectors can enhance the signal strength of a cell phone by about a factor of 5 and thereby extend the range at remote locations by about a factor of 2. The first reflector type shown here is simply a parabolic array of vertically oriented aluminum tubes held in place by a folding wood structure. This reflector is lightweight, wind-resistant, easily transportable, and does not require the use of any powered devices or cable connections to the cell phone. This slide depicts an incoming signal from a cell tower reflecting off the parabolic array and forming a hot spot where we can place the cell phone. The somewhat surprising thing is that there is very little signal leaking beyond the widely spaced tubes, and this simple fact is what makes it possible for this design to be both very lightweight and highly efficient. On transmit, the cell phone by itself has a very wide donut-shaped radiation pattern with a maximum directivity of about 2 decibels isotropic. By adding the reflector, the signal is focused into a narrow beam with a directivity of about 9 decibels isotropic. And when the reflected beam is directed toward the cell tower, we can expect about 7 decibels of signal enhancement, or equivalently about a factor 5 in terms of signal power. For use at remote sites, the low-frequency bands offer the strongest signals. The long wavelengths of these low-frequency bands enjoy inherently lower propagation loss, diffract more readily around corners, and allow deeper penetration into buildings. All 3 primary cell phone carriers provide low bands for service at the extended ranges encountered at remote sites. Here are 3 reflector topologies that were analyzed. The one on the left is the parabolic array of tubes and only enhances vertical polarization. The second one is a corner reflector made from a folding aluminum grid that works for any polarization. The third one is a parabolic cylinder that focuses slightly better than the corner reflector. This chart shows the predicted directivity for the 3 different reflector topologies. As expected, the parabolic cylinder provides the highest directivity, but all 3 provide more than 9 dBi of directivity over the entire range of low-band frequencies. A prototype of the parabolic array of aluminum tubes was built. As shown in the picture, it folds down into a compact size and has a total weight of about 12 ounces. A prototype of the foldable corner reflector was also built. This reflector is made from aluminum mesh and folds flat. The reflector itself weighs about 10 ounces and the cell phone holder weighs about 6 ounces for a total combined weight of about a pound. With some additional work, it could be made lighter and made to fold into a smaller package. Santa Rosa Island, located off the coast of Central California, provides an ideal location for testing these reflectors. As shown in the diagram, the cell towers are clustered close together in angle, and this provides an easy choice when it comes to deciding where to point the reflector. Additionally, this remote site has limited cell service and hence provides for realistic testing. The corner reflector prototype was selected for the initial testing since it is easily swapped in and out during the test without moving the cell phone. That way, we can clearly demonstrate the signal enhancement with and without the reflector. For these initial tests, the reflector was swapped in and out every 5 minutes over a 45-minute period while recording the signal strength. The signal strength was recorded by utilizing the Network Cell app. This app can store the signal strength over time and location. The campsite picnic bench served as a platform for the reflector. The signal path from this picnic bench to the cell towers involves diffracting over a ridge. This route can only be traversed by the low-band frequencies that we desire to test, and hence acts as a filter to remove any high-frequency signals that might otherwise interfere with the tests. The results show a dramatic enhancement of about 8 decibels as the reflector is swapped into the test, and a corresponding 8 decibel drop when it is swapped out. This was demonstrated repeatedly over the 45-minute period. In conclusion, the reflector does work. It effectively doubles the range of the cell phone. It is easy and cheap to build, but often walking to a location with better reception is more practical. And we need to keep in mind that a 1 bar change in signal strength on a cell phone relates to about 10 decibels. So our 8 decibels of enhancement is slightly less than 1 bar. This chart shows a couple interesting examples of similar work done by others. Both examples use a passive reflector to enhance signal reception without the need for any powered devices. The first example is the Australian hotspot that uses a large offset reflector to focus the cell signal onto a post where one can place their cell phone. The other example is a homemade windsurfer type reflector for enhancing Wi-Fi signals. And finally, thank you for listening to this video. If you have any comments or suggestions, please feel free to contact me via the email shown on the top of these charts.